So today I'm gonna tell you a trick, like especially if you're taking like calculus 2. Like in my university, the course code was 1014, yeah, that math 1014. And initially I was like quite bad in the midterm because I didn't do well in integration by parts. But eventually I found a video about integration by parts using the table method, like the DI thing, where you differentiate one side and you integrate the other side, and you have this like alternating signs. Yeah, so if you haven't know about the DI method, I highly recommend you to check it out. But the limitation with the DI method is that when you have an integral that needs different integration variables, like for example this integral x cubed sine x squared dx, like you can't just integrate sine x squared with respect to dx, right? You need to actually convert the dx to x squared. So another way to think about this is that you add a third column. So instead of just differentiating, integrating, and okay, sorry. So instead of just differentiating and integrating, you have a third column for the variable. Pop, pop, pop. Well, obviously you will integrate the sine x squared, right? It's because you want to get x cubed into 0 as you differentiate it, like the powers keep decreasing. So basically, the table method is just a smarter way to write integration by parts. Minus VDU. And what I'm doing here is that I'm writing this integral of u dv as this is u, this is dv, right? This whole thing is dv. Okay, and this is u. So if you take a look at this, it's 2x, and you can substitute dx with dx squared over 2x. So you can rewrite the integral, like currently this is the equation, right, that you want to integrate. You can rewrite the whole equation as so you can rewrite it as x squared over 2 sine x squared d x squared. So what I'm doing here, I'm just basically rewriting the equation, but I can also do that inside the table, So this is u and this is dv, which you will integrate. So instead of u being x cubed, I can turn u into x squared over 2 and dv as this whole thing, sine x squared dx squared. And now I can just do the usual table method. You know, like I differentiate this into x, and I integrate this part into minus cosine x squared. So when differentiating this part, the variable that you differentiate with, in this case is x, you'll put it here. You'll put it in the variable for the next equation. And then you can do the same trick again. You can substitute again, right? So you know that dx is equal to this, and then you can just rewrite it as half minus cosine x squared dx squared. And then do the differentiation and integration, becomes 0 minus sine x squared dx. Where does the dx comes from? You differentiate this thing, half, with respect to dx. Okay. Just by looking at this equation, you know, like the integration by parts equation, u, half is u, and you differentiate it with respect to dx, it becomes du, right? Yeah. Because when you differentiate it with respect to x, du dx is equal to whatever that thing is, right? And whatever that thing is the derivative, which is here, and du is equal to whatever this thing is, dx. So you put it here. That's what du is. But in this case, you can like rewrite the thing, I'll say, like, so you just move the order. So phi du is here, right? So you split the du into these two things, and you put the phi in the middle. Like, if that makes sense, you know. It's very hard to explain this, but it's very, very fast once you get the hang of it. Positive, negative, positive. Yeah, so the sign is just like the usual DI method. But the way that you take the answers is like the diagonal, just like the DI method, but you must cross the horizontal line, you know, like. So the final answer is minus x squared over 2 cosine x squared plus half sine x squared. Oh, don't forget plus c. Yeah. So the only reason that you want to use this method instead of the normal DI method is that when you need to do a change of variable, you know, like you change the, when you need to do substitution. All right, I think that's it for this video today.